Thank you, Rachel. Welcome to the Cortex Meet the Architect meeting for the month of July 12th, or date of July 12th, 2022. My name is Arie Hoeven, and I'll be presenting on architecting for the multi-actuator era. So today's agenda. We're going to start by introducing, we're going to start at the 10,000 foot view and start by introducing the multi-actuator era. Then we'll start going deeper into looking at multi-actuator HDDs, and then specifically the challenge of SATA as we move from a SAS-only product to SATA, which has new challenges. And some of those challenges we're meeting by making optimizations to the BFQ IO scheduler. We'll do a survey of what an IO scheduler is. We'll go into deeper detail into what we've changed in BFQ to architect for the multi-actuator era, and then we'll have some conclusions and a discussion. You know, as I'm going along, there's extra time here, so feel free to ask a question or raise your hand, but we'll try and keep most questions for this last section. All right, introducing the multi-actuator era. So as we're moving forward, if you look at this red line, HDD capacity is increasing, and it's always been increasing constantly, but now we'll be seeing a new generation of energy-assisted drives. And if you look at this red line, once we enter technologies like HAMR, heat-assisted memory recording, we start to see this this advancement, this increase in areal capacity and disk size increase at a more rapid pace. What you see here with the orange line is the nearline IOPS per terabyte, and nearline we're referring to, you know, the largest disks we ship to our cloud customers and others who are usually at that highest capacity point. And the primary metric of data accessibility for these drives is determined by IOPS per terabyte. You know, throughput remains the same as disk sizes get larger. So the IOPS you get per terabyte, which impacts your applications, your guarantees for latency, your basically performance of your drive is dropping rapidly, or dropping at the same rate as areal capacity and HDD capacity is increasing. So what we see here is there is a level at which, and this differs by customer, but there's a level at which something we call the IOPS wall, where your typical IOPS per terabyte is required. And there are a few reasons that's been pressing down, and we'll get to that in a future slide, but it's not dropping at the rate needed to keep up with this, you know, nearline IOPS per terabyte line you see in orange. So we see these new recording capacities. We're pushing to 30 terabytes, 40 terabytes, up to 60 terabytes plus in not too distant future. And you know, I give a sustainability presentation where I hold up one drive from 1996. You know, highest capacity at that time was around 1 gigabyte. I hold up, you know, this was last year, so in my other hand, I have an 18 terabyte drive from Seagate. And to compare the two, I would have to stack, to get the same capacity, I would have to stack that 1 gigabyte drive 5 football fields high, 500 yards high in the air to get the same capacity that I get with my the drive in my right hand. And that's what we get done in one generation. So you can imagine that we'll have these types of inflection points moving forward. And this is something I see as an inflection point. The servo mechanical capability is not scaling with this areal density. You know, we can't spin the drive faster for a number of reasons. You know, power consumption, it just doesn't scale. You know, it's not something we can't go from 7,500 to 20,000 RPMs, for example. You can't move the actuators aren't going to be moving faster. We've kind of met the physical limits there. So we don't have the capability, except for what we're going to be presenting today is the multi-actuator is really the only path forward. If you look at the patent activity online, you'll see that it's not just us, there's consensus in the industry that this is the path forward to meet this problem. Today, customers are, you know, if they have very high performance needs, they may be replacing HDDs with flash at a tremendous cost. It's much more expensive. They may be short stroking the HDD, only using the outer 50 or 75% of the disk to maximize performance and then stranding the rest of the capacity. And we see this a lot, they're just simply deploying lower capacity drives. There's still a market for 4, 6, 8 terabyte drives because it's still a lot cheaper than flash. And some customers need the IOPS per terabyte that those smaller drives offer. One problem there is that you don't see the price erosion at those capacity points that you see at the higher capacity points. All these things hurt TCO. So this is not a sustainable thing it's not a sustainable path that we're on. So the challenge is performance density. And there are other strategies, and we see especially our biggest partners, some of the big CSPs who have a lot of resources. They're really, really doing everything they can to squeeze the performance out of the drive, even with lower IOPS per terabyte. System level caching, up to it's a good strategy, especially for write performance, to have up to 10% of your storage be in flash for caching. After 10%, there's diminishing returns. Queuing with latency management, going to larger queue depths, and then making sure you're careful about managing latency. If you do it smart, you can get better seek efficiency. And then we have these other technologies, IO prioritization schemes, scale command timers. A newer one that's very popular that gives you a lot of control over having different classes of performance for different processes is command duration limits. And we could give a whole talk on that, but there's a lot of information out there. That's also allowing CSPs to make sure that their highest performance requirements are met, while other activities of an application that don't require a high performance can have lower latencies. And then longer transfer lengths is always a good strategy. So the solution is multi-actuator technology. And you have two actuators, can theoretically, or can in fact, especially for sequential workloads, double the drive performance of your drives because you're transferring data concurrently. If you look at this picture on the right, you'll see that the actuator is effectively sawed in half. So the upper half of the actuator is only addressing the upper set of platters, and then the lower actuator only addresses the lower region. No single surface area is serviced by two actuators. So we have these two distinct we call them upper and lower actuators on the drive, and that's how the technology works. And this is something that we really know how to do. As a hard drive company, we understand actuators, bearings, pivots, heads, preamps. This is something folks like us in the industry are very good at. And we're already shipping these drives at 14 terabytes, and we'll be soon at 18 terabytes. And we'll go into more detail there just briefly. This is an ideal solution today for things like content delivery, email systems, video streaming. Moving forward, we see it moving more, especially as we get to the other needs, other IOPS barriers for different classes of apps. We'll see it as software-defined storage, object store, Ceph, Hadoop, etc. So as we hurtle towards the multi-actuator era, this is another view where we've made a really hard attempt to look at some real data points on this line. And you'll see that there are a class of applications where they need 10 IOPS per terabyte. That's where you see the short stroking and the lower disk sizes today. Another line in the sand is 5 IOPS per terabyte, and that's where these strategies have pushed some of our biggest partners, to where they are able to deploy, 20 and even 22 terabyte drives without moving to multi-actuator. There is a point somewhere prior to 40 plus terabyte drives, where we're going to see this paradigm shift in the industry, where the predominant drive today is single actuator, with dual actuator is a niche, and with a few very important applications that need that performance today. That's going to flip to where at some point in the future, dual actuator and multi-actuator is going to become the predominant nearline drive in the industry, and single actuator is going to be relegated to archive and lower performance, lower latency types of implementations. So to put this succinctly, and I love how vice presidents think, but my senior vice president, Jeff Falkman, made this quote internally in a Seagate meeting. He said it succinctly that all that data cannot sit behind a single actuator. So if you're snoozing for the last 5 minutes, that's the key takeaway. So let's look at today's dual actuator drive. And this one we've been shipping for a couple of years. This is our 14 terabyte SAS only Exos 2X14, a drive we call the Harrier. It's a dual LUN SAS drive. So SAS has LUNs. So you can have one file system per actuator. And to Linux, this looks like one disk per actuator. So from a Linux device listing view that you see here, you'll see that this has two dual actuator Seagate drives, and then I think two flash drives. But you look at those two Seagate drives, it appears as four drives to Linux. You have SDA, SDB, SDC, and SDD. This, from a software stack perspective, is fairly simple. You just address each actuator like it's a drive. The application sees a single drive, the file system sees a single drive. The biggest thing you have to worry about here, and it is a significant worry for some customers, is you have to worry about failure domains. You can't have SDC fail over to SDD thinking they're two separate disks. So you have to make considerations around RAID and striping and other things. And there's some management software, especially in the OEM space, that has enough of a problem with this that we've actually been had inquiries about, can we do this with a single LUN, which is possible, but not something we're doing today. So the bigger challenge is we've sold SAS drives in the past. Starting this year, this summer, we have CTUs going out for our 18 terabyte SATA product. And SATA doesn't have dual LUNs. So there is a load balancing challenge that we don't have with dual LUN SAS. So with SATA, we have a single namespace. So we have a single LBA range from 0 to max LBA, but you have two actuators, and each actuator has its own separate channel and preamp. It's physically a different thing, but to the software stack, it looks like a single drive. So we have the upper and lower SATA LBA space. There are no changes to the I/O protocol. We do have in ACS 5 in T13 in the specifications, we do have a log page that the drive describes this mapping. And now in Linux, the initial support was introduced last fall. It was patched by Seagate more recently because there were some issues with it, and this is always a problem in Linux when you are, and it's a problem we have today where you are making changes to Linux prior to the hardware being widely available. But Linux now has the ability to expose what we call concurrent positioning ranges to the file system, to the application layer. So that now at least we have the opportunity with I/O schedulers and file systems and applications to query and understand where these address spaces begin and end, rather than simply assuming it's the first 50%, which is something we were doing early on in testing. I'll also note that this will be a collaborative effort with folks in industry we'll introduce in a moment, and also our own free open system software team, our FOSS team, which is a lot of the testing and investigations you'll see in this presentation. So like any resource, either we're able to manage this LBA space or it will manage us. And we'll explain that in a moment. So when you look at, how do we, so the key problem here is when you have this, what looks like a single drive, applications direct I/O in all kinds of ways, and it's very easy for us to only direct I/O predominantly to one LBA range, not the other. So we get this imbalance in performance, and we don't get that up to 2x performance promise or that dual actuator can deliver. And in worst cases, we actually get what we call actuator starvation, where an actuator is severely underused or even idle. So how do we address this? And there are a number of good places we looked at this problem, a couple of years ago, and this is specific to SATA. So if you look at the bottom here, we have this split LVA space. Same problem exists for single LUN SAS. So it says split LVA or single LUN. Applications can do a better job if they're aware of this split and they use the new Linux functionality, and none do today. An storage application can see these two drives and then direct I/O accordingly, and that solves part of the problem. So as we move to this new era, we expect to see applications affinitized to understand this split LVA range. The file system, it's difficult, and the file system does a lot of things, but certainly there's new work that can be done in the file system. The file system can also redirect I/O. So maybe that becomes, maybe storage applications don't change as much in their file system innovations that happen in the future to address this problem. Again, none of that work has been done today. A simple shortcut is to use, device mapper or GPT partitioning or LVM2 to effectively partition the drive into two, so that then you're presenting, two targets to the file system and storage applications. There are pros and cons to that approach, but that's certainly something that we're advocating for in certain scenarios. It's an easy solution that you can use today. It has we won't go into all the, this presentation isn't about that, but we have presented on this issue in the past, and something that we think is one strategy. But then we get to IO scheduler, and there you have the red arrow in bold, because that is what we're going to be talking about today. IO scheduler is well positioned to sort and prioritize IO, and that I think in combination with file system affinitization is a key strategy, and one that we've invested in. The SCSI subsystem is there for completeness, but it's not really a place to solve this problem. So let's get into the IO scheduler. And these following slides, I'm going to give a lot of credit to our consultant, who we've contracted with, Paulo Valente. He works for the NARO, who we contract through, but he's also a professor at the University of Modena and Reggio Emilia in Italy. So a lot of credit to Paulo. He's been, we've been working with him for over a year and a half, and he's been a fantastic partner in this project. I should also add that Paulo is the creator and the Linux maintainer of the BFQ IO scheduler. So let's take a look at IO schedulers. What does an IO scheduler do? Well, an IO scheduler decides the order in which IO requests are to be served. So it is really the arbitrator of who goes first, which is critically important for most scenarios. So, one great analogy that I'm stealing the slide that Paulo uses is a traffic cop at an intersection. And this is really good analogy for the dual actuator problem. So there are a few things, traffic cop decides which cars go, and just like an IO scheduler, he has certain priorities. Top of mind is high IO throughput. If you've ever been at a traffic stop, there may be a long line of cars in one direction and only a couple of cars in the other directions. And what the cop doesn't do is he doesn't simply let one car at a time through in each direction. Instead, he'll look at the longest line of cars and let maybe 10 or 20 cars through at a time while others wait. And then periodically he'll stop and let the cars in, maybe there's a single car waiting. Well, that car, for high throughput, you just let that car sit there forever. But we also have to manage for low latency. So occasionally he has to make sure that those cars in the shorter lines are also let through, that they aren't waiting too long. Another goal of an IO scheduler is, and BFQ does this for interactive applications. BFQ is the default IO scheduler for Chromebooks. And if you have a Chromebook, or I should say the Chrome OS, and if you have a Chromebook and you launch Chrome, it launches instantly. And that's a trick that BFQ uses. And I think here the example would be if an emergency vehicle were to come to the intersection, you could stop all traffic just for a moment, let that vehicle through, and then resume, keeping latency and throughput in mind, resume with the other traffic. Fairness is another goal, and then there's some other goals for IO schedulers. So what's important to our problem is, we needed an IO scheduler that gave us a good ground for giving us this per actuator load control. And we looked at the other schedulers out there. None is basically first in, first out, or FIFO. Good for some types of applications. It's one we test with when we're testing drives, for example, because it gives us kind of the cleanest look at IO. MQ Deadline is a very well-respected and popular IO scheduler used by many of our, it and variants of it are used by many of our largest cloud customers. Kyber is another one similar, and then BFQ. And BFQ is the one that gave us the richest control plane infrastructure. It gave us the most knobs and buttons that we could use to tackle the problem we have with SATA dual actuator drives. Let's take a look at BFQ infrastructure. Again, credit to Paulo. Processes are being sent down from the file system and the applications. For our purposes, these are read-write. These are translated into IO requests and sent to the scheduler. And what the scheduler does is it divides these into flows. And each flow is sent into a dedicated queue and then scheduled with a given logic. And this is typically an elevator logic. So if you get on an elevator, you get on floor 1 and you press 15, and that elevator keeps moving until you get to floor 15. And may stop at 5 or 8 or floor 12 on the way. But what it doesn't do is it doesn't take you to floor 12 and take you back down to floor 5 because someone's pressed a button down there. It keeps going until it completes that path. And then it starts over and goes to the next new request. And that's kind of how each of these queues works. Then it's put into a flow service loop, and with a given logic, it's ordered. And we have following slides on that. And then once it's dispatched, it's sent back again. Let's look at these queues and service loops. So BFU does treat these differently. It treats the IO of each process as a separate IO flow, as you saw in the diagram before, places it in a separate request queue, and then there is a weight associated with each process and queue based on certain logic. So as we're going along, each of those queues you saw is serviced for a while, but not always in a strict order. So here you see Q3 being served, then Q7, and then Q3 again, because it has a higher weight, and then maybe Q2, and so on and so forth. So this isn't a strict ordering. Everything, there's a logic here, and it's looking at the bandwidth share of each queue proportional to the queue's weight. So now we have a problem. Let's say we have 2 actuators. It's very easy to schedule the one actuator starving the other out, and there's no guarantee of any load balance between the 2 actuators. So in a given queue, you may even generate work for both actuators. And in this case, you see the lower actuator is Q3, Q7, Q3 again. Then we get to Q2, and you have a mix of IO for the lower and upper actuator. And one of the key problems we have, or challenges we have with SATA, is there are only 32 queues available to a SATA disk, and that means only 16 per actuator. And on a SAS device, you have 254. So we have a very shallow command queue depth, and it's very easy for one process to quickly consume all 32 of those command queues, and then there's no command queues left over for the other actuator. So we can actually get in a scenario where there's a severe delay in dispatching IO. So this is a look, and this is a heat map developed by a Seagate architect, testing done by our FOSS team, where we are in a scenario where we have a SATA drive and it's being fed an unoptimized, unmodified BFQ IO scheduler. And what's happening here is if you look at this heat map, here on the left, you see upper Q depth and you see lower Q depth along the lower axis. And a simplistic way of looking at this heat map is for the upper actuator, the upper Q depth, we're at 32, so it's actually consuming all 32 of the command queue, the hardware command queue, and you're getting a lot of I/O on this one actuator, and then over here on the heat map on the right, you're getting a whole lot of zero. You're just not getting any activity at all. So we've completely idled one actuator during the time frame here, where there's very little activity. I see down here in a couple of areas, but we've effectively, I should say at the top, this is a whole lot of zero. On the right, this is a whole lot of 32 for the upper actuator. We've effectively idled one actuator. So instead of seeing the promise of 1.8x or 2x performance that we can get with sequential workloads, in this case, and this is a random workload, we're effectively seeing something close to no performance gain for dual actuators. And this is running an FIO script. We aren't purposely, and we've done testing with purposely sending imbalanced workloads, but this isn't it. We're feeding both actuators the same amount of work. So there's a need to control actuator load, and the ideal place to do this is the IO scheduler, which can sort and prioritize work if that IO scheduler can see the full view of both actuators. So this was the first step, the base idea. The base idea was, instead of having one queue for each flow, to have two queues. So each flow would have a queue dedicated to each of the two upper and lower LBA ranges, two actuators essentially. And each process is associated with n number of queues, one for each actuator. Here at Stukes, we're a dual actuator today. And then the service loop guarantees that all queues are served. So let's see the heat map after we tried this idea. Well, now we are getting work to both actuators, but every time an actuator is busy, it is consuming all 32 of this very shallow command queue for SATA. So effectively, we're in two equal probable states. So either only the upper or only the lower actuator is busy. Why? Well, this is what's happening. We're actually servicing one queue at a time. So the workload is made of two read streams, and we're simply cycling between the two. So Q1, upper actuator is idle, Q2, lower actuator gets idle, and so on and so forth. So a new problem. So there may even be a more severe scenario where instead of going, alternating, we actually have a time period where it's only one actuator, and then only occasionally do we keep the other actuator busy. When we did testing on this, we did see some performance improvement, over the first, unmodified BFQ, but we still didn't see the type of performance we were hoping for because of this problem. So Apollo and Seagate architects came up with a brilliant idea, and they said, well, why don't we reserve a certain number of hardware queues that can only be serviced by each actuator, so you can never dominate all 32. And we call this injection. So while a service queue contains I/O for a given actuator, we then inject or dispatch I/O for other actuators. We make sure that both actuators are busy effectively. And that way, even if you have a workload that's predominantly sending I/O to one half of the LBA range, we make sure that the other actuator is kept busy with whatever work is available. Even if that work is not as highly prioritized, we are now prioritizing based only on the domain of that LBA range of that actuator. So we came up with a number. Currently, the number we settled on was 4. And having 4 command queues of the 32 available is a really good number for sequential workloads. You only need 2 or 3 command queues to keep an actuator fully busy with sequential workloads, and even with random workloads with smaller I/O, we found that we generally get something close to 75% performance out of that actuator as long as it has access to at least 4 hardware command queues. In the future, and testing the FOSS team has done, we found a variety of results. For the purposes of not having a 3-hour presentation, we're not going into all that detail. But in the future, there may be opportunities for say big CSPs to modify that and say, well, in our scenario, we want 6 or we want 8 of the 32. There is also, we see this a lot in certain markets, especially a lot of CSPs will take a Linux I/O scheduler and modify it for their own use. So BFQ is providing an excellent template for that type of custom I/O scheduler. So now that we are guaranteeing at least 4, we are getting what is more ideal. And an ideal scenario would be upper left to lower right having just a good diagonal line, which we do see in some of our testing now that we've made this change. In this example, we see a lot of work happening here in the upper queue depth and at both, say, 20 or 28, and then again at 4. And likewise for the lower actuator, we see work being done at both 28 and 4. So that's how to read this heat map. So now both actuators are consistently busy. This is, again, a random workload, 4K I/O with 80 IOs in flight for each actuator. Of course, they can't service all 80 at any one time. And this is giving us, really excellent performance numbers and a great improvement over, what we started with. And here's a look at that. So this is again, we just took one result out of many that we have available, but it's representative. We have 4K sequential reads with 80 requests in flight per actuator again. Using and this surprised me, but using the none IO scheduler, for whatever reason, it doesn't do well on dual actuator. The early BFQ, before we started modifications, the legacy BFQ that's still default in Linux today, although we have submitted this new BFQ about 2-3 weeks ago for the latest version of Linux. So hopefully at some point in the next month or so, it'll be available as part of the Linux distro. But the original one, the ones there today, doesn't perform well. Then the MQ deadline and Kyber IO schedulers, for whatever reason, do much better today on dual actuator drives. But then once we made these changes, we saw a dramatic improvement in BFQ IO scheduling performance and a 25% higher throughput than the best performing next scheduler, which here I think in this one it's Kyber. Sometimes it's deadline depending on the test we're running. And we're also seeing very stable performance. And that's because BFQ has a lot of control. So we're seeing much less variations in things like latency. So we really love the results and the stable performance that we're getting with the new modified BFQ, which we hope will soon become part of the Linux distribution. So in conclusion, we are entering the multi-actuator era. This is a huge paradigm shift for the industry and for the Linux software stack from top to bottom. We should not forget Windows. I'm myself a former Microsoft employee. I worked on the Windows kernel team, and I have a lot of confidence in Microsoft Azure and the Microsoft Windows Server team to see the same types of problems. And they are one of the ones who are an early adopter of dual actuator. So we should call out Windows here as well as someone that we expect to see adapting to this new multi-actuator era. These drives are going to drive an evolution in Linux storage stack innovation. So as soon as we get past that tipping point, that inflection point of moving from single actuator predominant to dual actuator predominant nearline drives, you're going to see a lot of activity. We've been out here giving presentations for 3 years at the Storage Developers Conference from the SNIA puts on every September. We haven't gotten a lot of attention yet, partly because nobody's feeling this problem yet, or very few are, I should say. That's going to change in the next couple of years fairly dramatically and fairly quickly. Those who fall behind are going to not be competitive with TCO. That's a huge, huge gap if you're in the nearline business. BFQ IO scheduler is really the first one to tackle this problem. It's leading. You know, I see a perfect world of IO scheduler optimizations along with application and file system modifications that will follow. And there are opportunities out there for development with organizations that lead the way. So that concludes my presentation. And I see there are members of our FOSS team on board, and I'll go ahead and open it up to questions or discussion.
My name is John Seikerbike. I shared a link in the chat. So about a year ago, I wrote a paper researching the SAS version of this, the dual actuator drive, and I'm sharing that with the folks here. The problems were different than what we would see with a linear address space on SATA, but I totally concur with all your observations and followed in your footsteps maybe a little bit about a year ago. So and ironically, under the context of SAS and multiple LUNs, I was able to outperform BFQ with the no-op scheduler. And the challenge for us is really with this dual actuator. Sequential writes aren't a problem, but updating metadata synchronously is a problem on a file system. And as you point out, the failure domain has to be maintained. And the most significant challenge for us is the, as you've indicated with the BFQ scheduler work, is on read workloads, keeping those actuators synchronized. In that paper that I shared, I used some LVM tricks that worked exceptionally well for everything except ZFS. And there's case studies of leveraging Mach 2 for Ceph, where the performance was absolutely stellar. There's case studies for XFS and a couple of other deployments. But the key to everything except for ZFS was in leveraging LVM to build a topology that respected the failure domain of the single drive slot while tweaking parameters for the scheduler. And in my case, it was the no-op scheduler, such that you're basically assured that the LVM layer was doing the multiplexing to the dual actuators in such a way that left, right, left, right, left, right, and they didn't get too far to sync. Where we ran into some serious troubles is the fact that the physical topology on all of those platters may not be close enough to being the same. And again, the read workloads are the challenge with that. And my approach on that was simply limiting write merges at the scheduler, which is common to all these things, and also increasing slightly the read ahead queue in the disk schedulers. And so anybody on this call, you can get my contact information, and I'm happy to pair up with anybody later on, share what I did. The work I did was SAS, but this is a problem that's still very near and dear to me, and I am a hardcore proven believer in the dual actuator technology because I've proved it to myself. So thank you guys for all your great work. We're turning it into applications out there.
Thank you, John. And you make a great higher level point that I probably glossed over, is that, you know, even with SAS dual actuator, you know, the problem space we were looking at in this project, you know, was specific to SATA and the single LBA space. But, you know, there are all kinds of assumptions made about drive geometry and drive behavior that are broken even in the SAS model. And I think that's kind of the overall theme that we see, is that even with SAS, you know, we have sold a lot of the SAS drives, but to very specific types of implementations and deployments. And, you know, we're going to find that there is a similar inflection point and need for stack changes for SAS as well as SATA. Thank you. All right, if there aren't any more questions, I may hand back to you, Rachel.
Fantastic. Thank you so much. That was a great talk. Let me quickly just share As usual, thank you for everybody who made it to Meet the Architect, and really great talk. Really glad to have you. If you'd like to know about all of our future Meet the Architects, please sign up for our newsletter. It can be found at cortex.link/newsletter. And you can, of course, poke at the Cortex project if you'd like at cortex.link/GitHub. So I hope to see everybody again next month. Thank you.
Thank you.